Commander King here with another mission. Right now we're looking at comparing sodium and cesium to create hydrogen gas. And I want to know which of these is going to be easier to remove an electron from. Now when I think of removing an electron, I'm thinking about the ionization energy, which is the energy needed to remove an electron. So I know that's going to be important. But I want to be able to back up that ionization energy. So just from looking at a table, I can say that cesium has lower ionization energy and is going to be able to easier to remove an electron from that. But I really want to know why. And to know why, we want to look at the atomic structure. So right now I've got sodium and cesium. I've written out the electron configuration, the entire thing, because that's going to help me visualize it. All right, so I'm thinking about sodium. So I'm going to draw a sketch for sodium here, a sodium atom. I know I've got my nucleus. I'm going to just do a brief Bohr model just to help me out here. I know I've got 11 protons and some number of neutrons, but they're not going to be that important for this. I know, according to this, I've got on my first ring 2 electrons, 1s2, so I'm going to put 2 electrons. I know on my second ring, I got the 2 electrons in the 2s and the 6 electrons in the 2p, so 8 electrons. And on my third ring, I've got 1 electron. Okay, wonderful. Now let's take a look at cesium. All right, so cesium is going to be a little bit more complicated. Well, because there are a lot more electrons. In fact, there are 55 electrons I have to put on. So again, I'm going to go through the same methods. Cesium has 55 protons based on the atomic number. And I'm going to start putting on my electrons. So I see the 1s2, 2 electrons. In the second energy level, same, 8 electrons. In the third energy level, I've got to be a little bit careful because I see I have my 3s2. And I've got my 3p6, meaning 8 electrons there. But way down here, remember those d electrons, even though in the fourth row of the periodic table, they like to drop down 1. And so they are actually in my third energy level. So I have 18 electrons now in the third energy level. Okay. Now in my fourth, I got 4s2, 4p6, and 4d10. That's another 18 electrons. Wonderful. And then my fifth ring, I got 5s2, 5p6, but no d, so I'm ending at 8 electrons. And on my last ring, my 6s1, I have 1 electron. So that's what my Bohr model for each looks like. And very clearly, I see a big difference between these two elements, right? Well, obviously, the cesium atom is going to be much bigger because there are so many more energy levels. The electrons are going to be further away from the nucleus. And that's going to be something very important that I make note of. All right. But one thing that can help me sometimes is also the effective nuclear charge, and I want to make sure I calculate that. So again, I want to calculate the effective nuclear charge, okay? And remember, the effective nuclear charge is how many protons an electron way out here. So if I have an electron way out here, how many protons does that electron feel are pulling on it? Okay, well, let's focus in on the valence electron, since those are the ones that are likely to leave. So in that case, Na, it's the one on the third ring. This one electron, well, how hard is it for that electron to escape? Well, I've got 11 protons pulling on it, right? So I've got 11 protons pulling on it. And now they theoretically are all pulling on it, but I've got these electrons in the way. I've got these shielding electrons that are blocking. You know, the protons are trying to pull these electrons in, but I've got these 2 on the first ring, 8 electrons on the second ring that are shielding those from that outer electron from being pulled. And so I've got to subtract that 10. And what I end up with is an effective nuclear charge of 1. Okay, just an estimate. There are other factors involved, but for all intents and purposes, it's about 1. All right. Now let me do that for here too. All right. Well, this time I'm still looking at the valence electrons. How difficult would it be to pull off? Well, this time, even though it's further away, I've got 55 protons pulling. So that's a lot more protons than sodium. But look how many electrons I have shielding. I have 2, 10, 28, 46, 54, 54 electrons shielding. That's a little rusty. 54 electron shielding. And so the ENC is also 1. So in terms of the effective nuclear charge that I'm seeing here, it seems that both valence electrons feel the same amount of pull from the nucleus. In other words, they feel 1 proton pulling on it. So this isn't going to help me explain which one is easier to remove, because according to this, they're the same. Okay, so that's not going to help, but I'm glad I calculated it. I've drawn the Bohr model. And now I just need to make an argument which will be more reactive, or which will be easier to pull an electron from. Okay, and for this, I'm really going to focus on the size. So I know sodium is a smaller atom, right? So this electron is a much smaller atom, which means these protons, okay, are much closer, right? Because it's such a small atom, and what that means that they're able to pull that electron more. In other words, the further electron, the harder it is to grab it in. But if it's closer, it's going to be easy to pull that electron in. Whereas in cesium, this electron is way out there, right? It's way out there. And so I'm going to have a difficult time, if I'm the cesium nucleus, pulling that electron in. All right, so the argument I want to make is that cesium, okay, is more reactive. It is easier to remove its valence electron because, and here's the key thing, because the electron is farther away from the nucleus than in sodium. And this would be a perfectly acceptable, reasonable kind of thought. You might want to add in that cesium also has lower ionization energy, which means it takes less energy to remove, and we can get that from data. Okay, so that's one way to compare sodium and cesium and determine which one has lower ionization energy and why. King out.